Good morning. Once again, in this session, I would like to demonstrate the use of equation-oriented approach to carry out process simulation. As you can see, this is a problem involving rad-frac column, a rigorous distillation column, rating mode. The feed is 40% propane and 60% isobutane, entering at these conditions of temperature and pressure at a flow rate of 1 kilomole per second. And there are other details, the feed stage, total number of stages in the column, and so on. The issue here is we are required to obtain a purity of 98% with respect to propane in the top product and 99% with respect to isobutane in the bottom product. Remember, especially when you are using a model which can perform rating calculations, we will not be in a position to give this information while defining the problem because they are with respect to the output streams. So information with respect to the output streams is not accepted in any rating model. So let us see how to handle this problem using equation-oriented approach in Aspen Plus. So the two components that we are dealing with are propane and isobutane. So define the components. Let me call this as IB. Go to the next step. Select a property model, maybe Chavo Cedar. Go to the next step, simulation environment, create your flow sheet. If you are not experienced with rad-frac column, what I suggest is go through some of the demonstrations with respect to columns and then try to look at this problem. So I am providing the feed stream, the top product and the bottom product. Okay. Now let us go into the problem definition. So let me choose the unit system as SI. So the feed is entering at 322 Kelvin, a pressure of 20 atmospheres and a flow rate of 1 kilomole per second, having composition of 40% propane and 60% isobutane. So having defined this input stream, we may have to provide some data with respect to the block. So we are using equilibrium staged approach. So the total number of stages are given to be 22. Let me select the condenser as total. Then we don't have any idea about the distillate rate and reflux rate used in order to get to the required purities of the top and bottom products. So as a wild guess, let me assume this to be, let us say, about 0.3. It could be anything. And the reflux ratio has to be, of course, more than the minimum reflux ratio in order to achieve the required specification. Again, let me guess the value of about 2.5. So with this, we have specified the configuration. Now let us see what other information is required in rad-frac column. So we need to define the feed stage location. We were given that it is 15. Next. For the time being, let me assume that the pressure drop is across the column is 0. Is 0, there may not be any flow. In reality, there has to be some pressure drop from tray to tray or from top to bottom. Right. So within these limitations, now I have completed the required problem definition to carry out this rating mode or sequential modular approach. So we'll be able to run the problem in sequential modular approach. So we got to some results. Let me go to the stream summary and look at the mole fractions. Now we were able to get a mole fraction of 88% of propane in the top product. Remember, H2 happened to be the top product, and about 81% with respect to isobutane. These are not as per our requirement. Now you can probably use two design specifications in order to get to the required purities of the top product as well as the bottom product by manipulating certain variables. According to the problem, the manipulated variables are also given to you. The reflux ratio and distillate rate, which we have started with a wild guess, which resulted in some purity. The purity happened to be about 88 or almost 89% propane and 81% isobutane in the bottom product. Now let me, having run this problem once in sequential modular approach, I should be able to run it and switch over to equation oriented approach. So having done this, now I will be able to create a spec group, say new, then go to the next step. Be careful in selecting these variables. We wanted to obtain a purity of 98% with respect to propane. Right now we got about 89%, 0.89. So go to that value. Remember, this value is being calculated when you run the simulation in sequential modular approach. So I think this is the 1.88946. S2 happened to be the top product. So stream, propane, fraction. So this is the variable that I am interested in. So let me select this variable. Earlier, remember, this is being calculated, being a variable associated with the output stream. Now I would like to provide information with respect to this. And the value that I am looking at is 0.98. What is the physical type? You can say maybe contents, and units, there is fraction, so it will not have any units. Right? Now, in order to achieve this, you can manipulate the reflux ratio, which we have given initially as 2.5. We go to 2.5. So care must be taken in order to identify appropriate variables. So you can see reflux ratio is 2.5, which we have provided as input because this is constant. So this is the value I am interested in. Okay, select this variable. Earlier it was being provided as input. Now I would like to calculate. In other words, for obtaining this purity of 98% propane in the top product, I am asking the simulator to come up with an appropriate reflux ratio, which was originally assumed to be about 2.5. So remember, this is going to be calculated. So this is also contents, and it is also a fraction, or maybe percent reflux ratio fraction. Right? So let us run this problem. Now, for the time being, I am addressing the purity of propane only in the top product. Then after this, we will see how to handle the required purity with respect to the bottom product. We were able to come to a solution. Let us look at the stream summary and mole fractions. So we got to our requirement with respect to 0.98. So we were able to get the required purity of propane in the top product, but still we were not able to get to the required purity with respect to the bottom product, right? Reflux ratio gave this particular purity. Of course, these are available in the stream results. Remember, the reflux ratio we have assumed as 2.5, but only when the value of reflux ratio is 3.82, we will not be able to get to the required purity of propane as 98%. Now, in the same way, I will be able to talk about the other purity that we may be interested in. So I'll go to spec group, say new. I am going to create another spec group in order to address the second requirement with respect to the purity of the bottom product. Say new. You need to select the second spec group. Now, once again, as we did with respect to propane mole fraction, we wanted to calculate the 10 mole fraction in the bottom product. I think we were getting that at around 0.84 or so from the previous results. So you can see we want isobutane. Yeah. This is in stream 3, which happened to be the bottom product, isobutane fraction, mole fraction of isobutane in the bottom product. You can see the physical type is contents in case of fraction. So that's why I am selecting this as contents. This is being calculated earlier. Now I would like to make it as constant. So select this variable. I would like to provide this as input. What we require, 0.99. Physical type, contents. And the units, again it's a fraction. Now what is the variable you would like to manipulate? We have assumed the reflux, 0.3. We are already manipulating the reflux ratio. So I would like to manipulate the distillate rate in order to achieve this purity. Distillate rate has been given to be 0.3 initially. So let me see where is 0.3. Yeah, you can see the distillate rate kilomoles per second has been initially taken as 0.3. Now I would like to select this variable and calculate this value required to obtain this purity. Again, this is the flow rate, mole flow. Units kilomoles per second. So now we have two spec groups, each one talking about the first one is going to ensure required purity of propane in the top product. The second one is taking care of maintaining the bottom product purity in the bottom product purity with respect to isobutane. Remember, the distillate mole flow and the reflux ratio can both of them might be defining the purities. So it has to find out a solution which is acceptable by both these specifications. Of course, same thing would be true even if you are using a design specification or two design specification loops. So let me run this problem. So we were able to come to a solution within a practically very less time, but let us see whether we were able to get to our requirement. Now you can see we were able to get to the requirement of top product purity as well as bottom product purity, right? But what are the results that gave us the respective values of reflux ratio and distillate rate? Now you can see the reflux rate earlier was found out to be I don't remember, 3 point something, and the distillate rate we started with 0.3 but 0.40206, and combination of distillate rate and the reflux rate is going to give you the required purities. Remember, the distillate rate and reflux rate also may be dependent on each other, so it has to come out with a proper set of values for these two variables in order to get to your required purity. So in this way, you should be in a position to look at whatever requirement that you have, right? Especially when you have more than one design specification, the sequential modular approach might prove to be ineffective in reaching a going to lead to iterative solution of the rating model repeatedly, right? So in this way, depending on your requirement, you should be in a position to switch over to equation-oriented approach in case if you are dealing with more than one design specification, that too within a recycle loop. So depending on the complexity of the problem, you can exploit the facilities of equation-oriented approach in Aspen Plus. So with this, I would like to close this session.